Hi everyone. So now we are going to start studying about the characteristics of logic families. So there are certain terms like fan in, fan out, propagation delay, power dissipation, figure of merit, noise margin. So you should know the meaning of these terms. What do you mean by these terms? Because they might be used somewhere in your examination or in some questions. Directly from this question is coming, that is very rare. In ESE examination the questions can come in 1 mark or 2 marks, sorry, in 2 mark only it would come. So in 2 mark in ESE examination directly question can come, but in GATE that is very rare. But these terms can be used in some of the options. These terms can be used. Okay, so understanding the meaning is important. We will start studying about one by one. We will start with fan out, then we will see fan in, propagation delay, power dissipation, figure of merit, and then noise margin. Okay, but before starting, let's see one thing. Let's just say this is a logic gate. If my output is high, then I will call it high state. Okay, if output is high, I will call it high state, and if output is low, I will call it low state. So if output is high, this resistance is connected at the output node. So this is driving 5 by R current, right? So from output the current is getting out, right? From output pin, this is your output pin. From output pin current is getting out. So this is known as sourcing the current. Sourcing the current. That means it will source the current. Okay, if the current is getting out, that is known as sourcing the current. Okay, so output current when state is high. Output current in high state. So what did you understand here? In high state, output source the current. Output sources the current. What will happen in low state? In low state, minus 5 volt is there. This is R. So this will take the current, right? So in output pin, current is getting in. Current is getting in. So output current in low state. Output current in low state. Output current in low state. Okay. So what do we mean? In a low state, this is known as current sink. They are sinking the current. In low state, output sinks the current. Now let's just say some other logic device is connected here. Some other logic gate is connected. So what will happen in low state? So output is low. That means input of this logic state is low. Output of this logic state is low. That means input of this logic state is low. No, let's just say I call it X and this as Y. So if output of logic state X is low, that means input of logic state Y is low. Now this guy is sinking this current IOL. So certainly this guy will be delivering the current. If IOL current this is receiving, forget about this load. Okay, forget about this R. If IOL current is getting in the output, that means this IOL current would have been coming from the input of logic gate Y, right? So if the input is at low state, then it will source the current. Just the opposite. In low state, input will source the current. In low state, input sources the current. That means in low state of output, the current is getting in. So certainly it would be driven by some of the input of some other logic gate. In this case, it is driven by the logic gate Y. So if the input is low, if my input is low, that means I will source the current. Say yes or no. So what I'm gonna write here is that in a low state, input sources the current. Very simple thing you would be able to remember, right? Most of the time it is directly written that in low state it sources. The reason is this only. If high state is there, that means it will drive the current. High state is there, it will drive the current. And here if I connect a logic gate, that means this driven current will be going into the logic gate. So if my input is high, that means I will sink the current. If input is high in a high state, if input is high, in high state, input sinks the current. Very easy thing. If you forget it, then you will be able to visualize the diagram. Okay, if output is high, that means current is getting out. So if current is getting out, to the next stage it would be getting in. So in high state, output sources the current and input sinks the current. In that manner you will be able to remember it. And in low state, output sinks the current and input sources the current. That's it. Okay, so the meaning of this slide was only this much. Let's start studying about fan out. So what do you mean by fan out? So if I am talking about fan out, so I am talking about fan out of logic gate A. So fan out of logic gate A is defined by the number of logic gates that can be connected to the output of this particular logic gate. Output of this particular logic gate is connected by two logic gate X. So fan out of this, no, this is how you do not define fan out. So you define fan out, that means how much input of logic gates can be connected. So if I am saying that the fan out of logic gate is 3, when input logic gate X is connected to its load, that means it can maximum take 3 logic gates at its load. Maximum it can take 3 logic gates. That means it can take certainly 2 as well. It can certainly take 3 as well, but it cannot take 4. This is the fan out. At the output of the logic gate, maximum number of some logic gate X could be connected. That is 3. So how do we define that? What should be the maximum number? Look, fan out is not a characteristics. Fan out is not a characteristics of any logic gate. That means in data sheet you will never see that the fan out of logic gate is 3. They will never write down this thing, that fan out of logic gate A is 3. Now, it depends on what is connected at the output. If logic gate X is connected, then fan out is 3. If logic gate Y is connected, then fan out could be something else. So how do we define that? Let's check that out. So we will take two states, when output is high, when output is low. So high state fan out of logic gate A. That means output is high. Output is high. So if output is high, then what it will do? It will source the current. So this I am writing IOH. And if it is sourcing the current, that means they will sink the current. So this is the input current when output is high. If output is high, that means this input will be high only. Because if I am having 5 volt here also 5 volt, here also 5 volt, here also 5 volt. So it will sink the current. It will sink the current. It will sink the current. Now what do I say? For the proper operation of logic gate X, for the proper operation of logic gate X, it at least need 5 milliampere current. Okay. For the proper operation of logic gate X, it at least needs 5 milliampere current to the input. Now what do I say? The maximum current logic gate A can deliver is 20 milliampere. In the high state, the maximum current this logic gate A can deliver at the output is 20 milliampere. In high state, the minimum current required by the logic gate X is 5 milliampere. That means how many logic gates you can connect here? 20 milliampere divided by 5, right? Because this is driving 20 milliampere current. Each want 5 milliampere, 5 milliampere, 5 milliampere and 5 milliampere. So each will take 5 milliampere. So 4 I can connect. Let's just say if I connect 5, then what will happen? So 20 milliampere will come from here. 20 milliampere will come from here. Now how much this will take? If I have connected 5, that means this will take 4 milliampere only. All will take 4 milliampere. All guys will take 4 milliampere. But it needs 5 milliampere to work. So that is not possible. So what do you understand by fan out? The maximum number of gates that you can connect. If I connect 3 as well, then also it is fine. That means it will not drive the maximum current. If I have connected 3, what I will see? I need 5 milliampere current here. So 5 milliampere, 5 milliampere and 5 milliampere. That means total 15 milliampere. So this will drive 15 milliampere current only. If I connect 3. But here I have connected 3, that means I am calling my fan out as 3. So what will be the formula of fan out here? So simple formula of fan out would be what? Fan out. But here I will be writing fan out in high state. So better I will write fan out in high state. Okay. So that would be IOH maximum. that this is the maximum current it can provide. That let's just say if it is 20 milliampere, and what is your I in H, that how much current it needs. If it need 5 milliampere, then 20 by 5. Okay, well, let's just say if IOH by 15 IOH was 15 milliampere, that means in high state I can provide a maximum of 15 milliampere. Then what is the minimum, and maximum current I can provide is 15 milliampere, and the minimum current it requires is 5 milliampere. Then what would be the fan out? 3. So that is the condition. I hope you must have understood. Very easy thing, very straightforward. By the way, I have beaten my sleep cycle. Okay, today I woke up at 6 a.m. Otherwise I go to sleep at 1 p.m. not 1 a.m. that is pretty bad. Okay, you should not try these kind of things. Okay, yeah. So now in the similar way, low state fan out could also be there, na? Like we saw the high state fan out, low state fan out could also be there. If output is logic low, then what will happen? It will sink the current. If output is logic low, it will sink the current, right? So that means they will source the current. If it is sinking, that means they will drive the current. So when input is logic low, how much current they are providing? When input is logic low, so how will the fan out will be decided? So fan out will be decided for low state. So maximum current it can take divided by the current it will provide. What do I say is that in low state, this guy logic gate X will provide 5 milliampere, and the maximum current this logic gate A can take is 15 milliampere. The maximum current I can take is 15 milliampere. If you apply more than that, then there is an issue. So maximum current I can take is 15 milliampere. And in low state, how much current you are providing? 5 milliampere. So what is my fan out? 3. Okay. Now it may happen that fan out low and fan out high can be different. Okay, it can be different. So what will be your final fan out? What that would be? You will take the minimum of why minimum? Because let's just say if this value is 3 and this value is 4. So what this guy is saying, that you can connect at least 3, and what this guy is saying, let's just say 5, and what this guy is saying, you can connect at least 5. So if I listen to this guy that I can connect at least 5, then I can connect 4 as well. If I am listening to this guy, that means I can connect 4 as well. If I connect 4, then this guy will not be happy. But if I listen to this guy, that means maximum I can connect 3. So if I connect 2, then this guy is also happy, this guy is also happy. So our task is to make both of them happy. So whose I will listen to? This guy. तो मैं इसकी सुनूंगा ना? I will listen to this guy, no? So that means always you need to take the minimum one, right? Let's see some question. It was a very straightforward concept, very straightforward. Let's see some question. For a TTL gate, you need to find the fan out. So how would you find the fan out? Always see the high one in high state. In high state, what was happening? In low state, what was happening? So always see high one. So these two are high, these two are low. So just you need to divide. The fan out will be, this can take maximum of fan out you need to find. So first I am finding fan out high. So 360 divided by 36, that would be 10. And what would be fan out low? It can take maximum of 18 milliampere. It can deliver maximum of 360 and they can take maximum of 36. Now it can take maximum of 18. This I should be knowing. 18 by 12, 1.5. So it is 15, right? So this is 15. So what will be my final fan out? Fan out will be the minimum value of these two. That would be 10. Okay. Very straightforward question. Very straightforward concept. Now this is a good question. For the following figure, each gate has I in H. I, what does that mean? Input current in high state. Input current in low state. In high state and low state, loading of output gate R. how much current they are loading. So this is what they are saying. So what do you understand by that? What is the input current in high state? When output is high, what they will do? They will sink the current, because if output is high, this will drive the current and they will sink the current. So they can take 20 milliampere, sorry, 20 microampere, 20 microampere and 20 microampere. So how much should be driven from here? So what is your IOH, output current in high state? That would be 20 micro into 3. So that would be what? 60 microampere. Next question. Solve on your own. What do you need to find? Input current in high state. Sorry. Output current in low state. So when output is low, so it will take the current. When output is low, it will take the current and they will drive the current. So how much current they are driving? When it is low, how much current they are driving? They are driving 0.5 milliampere current. When input is low, they are driving 0.5 milliampere current. So 0.5 into 3, this will take 0.5 milli into 3. This will take 1.5 milliamp. That's it. This is what they were asking. Okay. Let's see the next specification. Not specification, I should say characteristics, because fan out is not a specification. The specification is IOH max. This will be written in the data sheet, that maximum current it can take or deliver. But fan out will not be written, because fan out could be different, right? If I connect some other logic gate, it could be different. Let's just say if this logic gate was taking only 10 microampere. So if I was taking only 10 microampere and this was delivering 60 microampere, that means I could have connected how much devices there? I could have connected 6 devices there, right? And what if I say that the fan out of a logic gate is 6 and the maximum current in high state it delivers is 60 microampere? Then what will be the current it can take in high state? 60 by 6, 10 microampere. Or you can see that this is my logic gate X, and if I connect logic gate X only, at the output I am connecting logic gate X only. Here also this is logic gate X, and then output I am connecting logic gate X only. So this will deliver 60 microampere current, and fan out is 6, that means I can connect 6. So each can take 10, 10, 10, 10. Okay. So in that manner also you can think. So if fan out of a logic gate is defined, what does that mean? That across, if you at the input and output same logic gates are there, then I can define the fan out. That at the input as well and at the output as well I am connecting the same logic gate, then what will happen? The current it will drive, let's just say it is driving 60 microampere and I am saying fan out is 6, that means the same kind of logic gates you can connect 6. So 60 microampere, so each will take 10 microampere. Is this clear to you? I hope you are not getting confused. Okay, if you are getting confused, then drop it, otherwise it would be very easy. Just you can apply the formula. I was just giving you the concept that what is actually happening, right? Let's see the next one, fan in. So the maximum number of input you can apply. So if I am saying fan in of logic gate A is 3, so I can apply maximum number of 3 inputs. So this is fine, this is also fine, but this is not fine, because I can maximum apply number of inputs 3. You are applying input 4. Okay. Power dissipation. So in any IC, we studied about CMOS logic in last lecture. So there was this VDD, right? We gave the supply 5 volt, it could be 3 volt, it could be 0.8 volt, it could be 1.2 volt, it could be. So there was a supply, right? So from that supply, some current will get out. If there is a voltage and then there is a circuitry, so some current would get out. So that current I can call as IC. Okay. So what will be my power dissipation? Power dissipation, that I will call VCC into IC average. VCC value will be fixed. VCC into IC average. Okay. Now what do you mean by this IC average? So your IC average would be the current when output is high. The current when output is high. Okay. The current when output is high. So how I should write? IOH I should not write. Okay. IOH would be a different parameter. Just output current when output is high. So if output is high, so how much current is going? So ICOH I am writing. Okay. Now into duty cycle, if output is high, so into D plus output current when output is low, output current when output is low, into 1 into 100 minus duty cycle divided by 100. Very easy formula, you will be able to understand it. Let's solve an example. It will be very easy. So for a gate, supply is 5 volt. When output is high, it is driving 3 milliampere current, and when output is low, it is driving 2 milliampere current. Duty cycle is not mentioned. That means duty cycle is 50%. That means for 50% time it is driving 3 milliampere current. For 50% of time it is driving 2 milliampere current. So in a cycle, 3 milliampere, 2 milliampere, 3 milliampere, 2 milliampere, 50% time. So what will be your IC average? 3 milliampere plus 2 milliampere divided by 2. That would be 2.5 milliampere. So what will be your PD? 5 volt into 2.5 milli. So 25 by 2, 12.5 milliwatt. For a logic gate, VCC is 5 volt. IC when output high is 4 microampere. IC when output low is 6 microampere. The logic gate is operated with the output duty cycle of 70%. That means for 70% of the time 4 microampere was there, and 30%. What do you mean by duty cycle? Duty cycle is always associated with high time. That means if I am saying that my duty cycle is 70%, that means 70% of the time it was high and 30% of the time it was low. 70% it was high, 30% of the time it was low. So 70 by 10 it was high and 30 by 10 it was low. So this is what we mean by duty cycle. So 70, so VCC is already there. What will be my IC average? So 4 into 70% of the time it was high, so 0.7 I can write, and 30% of the time it was low, so 0.3 I can write. So 2.8 plus 1.8, what that would be? 4.6 microampere, right? So what will be my PD? 5 into 4.6. Micro is there, so answer will be in microampere. 46 into 5, 23 microampere. अरे यार microwatt. Okay, very easy thing. Propagation delay. So let's understand this by an example. So there is an inverter. This is my V in, this is my V out. So this is my input signal. From 0 to 1 it is going, but there is a finite rise time. From 1 to 0 it is going, but there is a finite fall time. I hope you know what is rise time, fall time. In very first lecture of digital electronics we have studied it. Rise time. From 10% to 90%, how much time it is taking. From 10% to 90%, how much time it is taking to come down. To go up, rise time. To go down, fall time. Now, what you are expected to receive at the output? When it was 0, 1. When it was going up like this, so it would come down like this. When it was 1, then 0. Going down like this, going up like this. And when it is 0, it is 1. So this is what you will receive. But there will be a slight delay. The same waveform you will receive, but with a slight delay. Because all the logic gates introduce some delay. Now, what is the 50% of this? This will be the nearly 50% of this. Wait. Color this. What is the 50% of this? Nearly this. Right? And what is the 50% of this? Nearly this. This is the 50%. 50% means 0.5. And this is also 50%. So, what is the delay in between them? But that means it was going high and it is going down. So if it was going high at t equals to 0, it is going down at t equals to some time. Okay. If I am assuming that it is going high at t equals to 0, that means it is going down at some time. So this is the delay. So this delay is known as delay when output is going from high state to low state. So TPHL it is called. propagation delay when output is going from high state to low state, TPHL. Propagation delay when output is going from high state to low state. Same goes for the next one as well. It is coming from high to low. 50% is nearly this, and this is going from low to high. 50% is nearly this. TPLH when output is going from low to high. So two kind of delay are there. What will be the propagation delay? Simply the average of both of them. TPHL plus TPLH. Propagation delay when output is going from low to high. Okay, very easy. There is a something called figure of merit. What do you mean by figure of merit? Figure of merit means propagation delay into the power dissipation into propagation delay. This is the propagation delay. This is known as TPD or TDE, whatever I have written. So here I will also write TD only, because in the previous slide I have written as TD only. So propagation delay into the power dissipation. Power dissipation into propagation delay. Okay. So what do you think? You will want a figure of merit to be high or low? You will want it low. Why low? Because you would want your delay to be also low and power dissipation is also low. Okay, don't get confused between power dissipation and power delivered. This is not power delivered. This is the dissipation power. That means it is eating up this power. This much power you need to provide. The supply is providing this much of power. So this is the user need to provide. So it is eating up the power. This is not something that chip is delivering. Chip is eating up this power, that is known as power dissipation. So chip is taking up this much of power. So you would want that your chip would take least power, right? And propagation delay should also be least. So if low FOM, that means better design. Now let's just say you want your chip to be very high speed. You want high speed chip. That means it responds very quickly. So you would want your propagation delay to be low. And if there is high speed, that means between 1 and 0 it is switching very high. 0 1 0 1 0 1. So the power consumption will also be high, because it is switching between 0 1 very fastly. So it will consume more power because it is working. So it will consume more power between 0 1 if it is switching. So if power consumption is more, that means delay is less. Delay less means it is switching very quickly. So power dissipation or power consumption is inversely proportional to propagation delay. Because if propagation delay is low, that means switching is very fast. If switching is very fast, that means power dissipation is more. So this is not the direct relation, just an analogy you can say. If you are having high speed of circuit, that means you are having low propagation delay. And if you are having low propagation delay, then there will be more power consumption. And the other side is also true. If you want less power consumption, then delay will be more. If you want less power consumption, then delay will be more. And if you want low propagation delay, then power consumption will be more. So somewhere in between you need to fix your design. That if I design a chip, then somewhere in between you need to be there, that either there will be less propagation delay. If there is less propagation delay, that means power consumption will be more, or the next thing is if there is less power consumption, then delay will be more. Okay, so somewhere in between you need to see the equilibrium. Let's solve a question. In a certain logic gate, VCC is 5 volt. You need to find the figure of merit. This much data is given, you need to find figure of merit. Okay, output duty cycle is 30%. Output draws a current of 3 milliampere when logic high, 4 milliampere when logic low. So let's find the power dissipation first. What is that? VCC into IC average. Okay, so what will be your IC average? 3 milliampere when logic high and duty cycle is 30%. 3 milliampere when logic high, duty cycle is 30%. So for the 30% of the time it is high, and 4 milliampere when logic low. 4 milliampere when logic low. So 0.9 plus 2.8, right? 3.7 milliampere. 2.8, yeah. VCC is 5 volt into 3.7 milliampere. So this will be in watt. And what about delay, propagation delay? So this should be given: transit from high state to low state and low state to high state. High state to low state 3 nanosecond and low to high is 5 nanosecond divided by 2. So what you are getting? 4 nanosecond. So this is the delay. So what will be your figure of merit? So 5 into 3.7 milliwatt into 4 nanosecond. So I will pause the video and solve it. You can also do it. Yeah, so it is coming out to be 74. So what will be the unit? Milliwatt into nanosecond. So it will be pico. What is watt into second? E equals to P into T. Watt into second. So what is that? Joule. So unit will be picojoule. Okay. So that's it. So we have studied what we started from. We needed to study this, so we have studied this as well, this as well, this as well, this as well, this as well. Now we are going to study this. What is your noise margin? Okay. So before that, let's understand a lot of terms. In the last we will study noise margin. Let's understand an analogy. Okay. So I am defining two level, that is 8 CGPA and 6 CGPA. अरे यार CGPA सही से नहीं लिखा हूँ, CGPA. Okay. Now what I am saying, to pass the examination you at least need 8 CGPA. So this is the line of pass. To pass the examination you need at least 8 CGPA. If you are getting above 8, then you are fine. Above 8 you are fine. So if I go to a backbencher, I will tell him that you need at least 8 CGPA to pass the examination. Okay, backbenchers will not be offended. I was also used to sit in the class in the last only. Forget about sitting in the class. I did not used to come to the class only. I never went to the college. Hardly in my complete B.Tech I attended less than 60 classes. You wouldn't believe it, but less than 60 classes. So don't get offended by the word backbencher. Okay. So if I go to a backbencher, I will not go to a topper. I will not tell him that you need 9 CGPA to pass, because I know he will get it. But what I will go and tell to a backbencher, that you need at least 8 CGPA to pass in the examination. Right? And if there is some topper who wants to fail, so what I will say to him, that you need maximum 6 CGPA. You can get maximum 6 CGPA to fail the examination. Right? So what is your 8 CGPA? Minimum CGPA to pass. It is value is high, but I will call it a minimum CGPA to pass. That at least I need 8. And what is this? Maximum CGPA to fail. That if you get above 6, then you wouldn't be failing in the examination. If you are between 6 and 8, you are in metastable state. You don't even know whether you are pass or fail. It's like JEE aspirants or GATE aspirants who are getting a rank around 1000. They don't even know whether they will go to IIT or they will have to take a drop. If you are getting rank above 100, you are fine. Above 500, you are fine. If you are getting rank below 3000, you are fine. But if you are between 1 to 3000, you are in the dilemma that whether you will take a drop or you will go to IITs. So that is this range. So the minimum CGPA to pass is 8 and the maximum CGPA to fail is 6 CGPA. Let's do this in the logic gate. So at logic gate we will apply input 1 or 0, right? Till now what we were considering, that 1 is referring to 5 volt and 0 is referring to minus 5 volt, right? But there has to be some certain threshold, no, that about 2 volt it will all be high and below 1 volt it will all be low. So that means there has to be certain threshold, right? that above this voltage, everything will be considered as high, and below this voltage, everything will be considered as low. So input value for low, input value for high. So what is your VIH? The minimum voltage, VIH will be the minimum voltage of input to consider as input 1. The minimum voltage of applied input to consider it as logic high. If I am saying that my VIH is 3 volt, my VIH is 3 volt. So if I apply 3 volt, it will be considered as high. If I apply 3.1 volt, it will be considered as high only. If I apply 4.2 volt, it will be high only. If I apply 5 volt, it will be high only. What is this? This is VCC. You cannot go above the supply. Let's just say my supply is 5 volt. So I cannot go above 5 volt. So this is your VCC. That from VIH to VCC, I can apply anything. Say yes or no. What is this VIL? Let's just say if my VIL is 2 volt. So if I apply 2 volt, then it will be considered low. If I apply 1.2 volt, then also it will be considered low only. So what is my VIH? The minimum value of input to consider it as a logic high. And what is your VIL? The maximum value of input to consider it as a logic low. So you cannot apply above 2 volt. So 2 volt is the maximum value. So if I had directly drawn this diagram, it would be confusing to you. But now it is all clear that this is the minimum I want to go up. This is the maximum I can take to stay down only. Same goes for output. In output as well, you will receive 1 or 0. In output as well, you will receive 1 or 0. No. In output also, you will receive 1 or 0. So again, in the output, the same thing will happen. This will be your VOH. Here I will write. This will be your VOH. And this will be your VIL. Now why, sorry, VOL. Now why I am making them lesser, like why this band is lesser, than you will understand. This is what is called noise margin only. Okay. So that you will understand. Don't have a doubt that, sir, why this band is more, why this band is less. So that you will understand. No need to worry about that. So what is your VOL? The minimum value of, what is your VOH? VOH is the minimum value of output to consider as logic high. That means what, let's just say if my VOH is 4 volt, this will be your VCC. If my VOH is 4 volt and if I receive 4.1 volt here, then I will get to know that yes, high output I am having. If I receive 3.2 volt here, I am not sure if it is high or low, right? But if I am receiving 4.5 volt here, I know it is high only. What about this VOL? Let's just say it is 1 volt. So if VOL is 1 volt, then I know if I am receiving 0.9 volt, then it is low only. If I am receiving 0.2 volt, it is low only. But if I am receiving 1.1 volt, I don't know if it is high or low. So what is VOH? The minimum value of output to consider as logic high. What is VOL? The minimum value of output, VOL is the maximum value. The maximum value of output to be considered as logic low. I hope it is all clear to you. Okay. So the words I have written, what is your VOH, what is your VOL. So VIH associated with input. So minimum input voltage which will be considered as logic 1. And what is your VIL? VIL is associated with input only. So maximum input voltage which will be considered as logic 0. What is VOH? Associated with output. So minimum output voltage to be considered as logic 1. And what is your VOL? O, that means associated with output. So not minimum, maximum output voltage, to be considered as logic 0, right? Now what do? I take an inverter whose logic levels I know, that at input what is the logic level, at output what is the logic level. So I take this inverter only, I know the logic levels, right? 3, 2, 4, 1 at input as well, at output as well. Now to the output of this logic gate, I connect another logic gate, the same logic gate I am connecting. So for this as well, I know the logic level. Basically, I know the logic level. This is the logic level here, this is the logic level here. So I know the logic level of this particular NOT gate. I know the logic level of this NOT gate as well, right? So if I connect them in series, or you can say if I connect them, if I cascade them, then what will happen? Now let's just say I have applied input 1.2 volt here. This is the input side. These two are identical, okay? Both are identical. Both identical. So both will have the same band, no? Input, output, both will have the same band. Okay. So here I am having 1.2 volt. So it will consider as logic low. What it will give me at output? Logic high. Logic high. For the output, what is logic high? 4 volt. So it should give me above 4 volt. Let's just say it is giving me 4.2 volt. If I am applying logic low here, I will receive logic high at the output, right? So logic high means something above 4.2 volt. Now it is being fed to the other logic gate. It is high, and as per the input, if 4.2 is high, as per the input 4.2 is high only, so it will give me low. It will give me low. At the output I will receive low. So at the output what should I receive? 0.9 volt. Right? If I receive 1.1 volt here at the output, then that is an issue, because output will read low as 1 volt. So at the output I should receive 0.9 volt. Say yes or no? Right? Now let's check one thing. So if this is happening, then this operation is fine. This operation is perfectly fine. Now let's check one thing. So here I was receiving 4.2 volt. There was no issue till then. Now let's just say some noise is added here. Some noise is added. Because of the noise, this 4.2 volt went up. It has went up to 4.5 volt. Because of the noise, it has went up to 4.5 volt. Okay. So what this input will take? This input will take 4.5 volt here. So again it is considering is logic high only. So if this voltage goes up, there is no issue. If this voltage goes up, there is no issue. But if this voltage goes down from 4.2 volt, let's just say it has gone down to 3.8 volt. Still there is no issue, because 3.8 is again taken as high only. This is the input side, this is the output side. So I will be looking at input side now. So input is again taking it high only. Now it is going down and it has went to 2.9 volt. Now there is an issue, because input will take 2.9 volt here and it doesn't know whether it is high or low. If my output was 4 volt, then I can apply high voltage anywhere. Let's just say from 4 it is going to 5 volt. There is no issue. Because of the noise, from 4 it is going to 5 volt. Still it will be considered as logic high only. But from 4 volt, if I had gone to minus 1.0001, that means because of the noise, this has reduced to 2.9999 volt. Then there is an issue. So what is the margin you are having? You are having a margin of 1 volt. If your worst case output could be 4 volt. If your worst case output has occurred, that means if 4 volt has occurred, then you have the maximum margin of 1 volt only. Because if the noise will take it more than 1 volt, if it is taking it down more than 1 volt, let's just say if it is taking it to 2.9999 volt, then input is not able to detect it. So what is the margin? This is the margin you are having, no? You are having a margin of 1 volt. Are you getting this point or not? So in between here, output state and input state, here only you check that I am having a margin of maximum 1 volt here. Right? If my worst case output has occurred, that means output was supposed to go high. So it has occurred 4 volt. It is high only. Now because of the noise, it can go down. If it is going up, there is no issue. Because if it is going up, there is no issue. But if it is going down, then there is an issue. Because if it goes down to 2.9999 volt, then my input of the other gate is not able to detect. Okay, so I have a margin of 1 volt. So this is known as noise margin, but it is in high state. Let's check for low state. Okay. For low state means I need to apply low input. Sorry, I need to apply high input. So let's just say any high input I am applying 3.2 volt. If I am applying 3.2 volt, it will consider as high only. It will give me low output. Low output, that means at least I need to receive 1 volt. At least I need to receive 1 volt. So if I am receiving 1 volt, if I go down, from 1 volt, if I go down, let's just say to 0.5 volt, is there any issue? No, it will take it low only. It has to take low, it has to consider it as a low, it has to consider it as low. So if I am going down, there is no issue. But if I am going up, if noise is being added, and let's just say the noise added is 1.1 volt, or better 1.001 volt, then what will happen? The input will go to 2.001, and if the input has gone here, then it will not be able to detect whether low input is applied or high input is applied. That means in case of low input, if I am going high, then there is an issue. Low input of this stage or low output of this stage. So here, if I need low signal, then I can go down, but I cannot go up. So how much margin I am having? 1 volt of margin I am having. So the maximum noise margin you are having, the maximum noise you can take is 1 volt. In case of 4 as well, if you are going down by more than 1 volt, then there is an issue. In case of 1 volt as well, if you are going up by more than 1 volt, then there is an issue. So the maximum noise margin you can have is 1 volt. Now let's just say if this was 1, okay, and this was 1.1 volt. So whose you will listen to, 1 volt or 1.1 volt? If I listen to 1.1 volt, then what will happen? I will say that I can have a noise margin of 1.1 volt. If I am listening, that final noise margin I need to decide. There are two noise margin, right? 1 volt and 1 volt. But if it was 1 volt and 1.1 volt, so whose I will listen to? I will listen to this guy or this guy. What this guy is saying? That if you are listening to me, that means noise margin you can have is 1.1 volt. So I will say the noise margin of this circuit is 1.1 volt. Now if I am receiving output 1, and because of the noise I am going to 3 minus 1.1, that would be 2.9 volt. Because of the noise, if I am going to 2.9 volt, is that okay for me? No, because this guy is saying you need to have at least 3 volt. So this is not okay for me. So if I am listening to the elder guy, that means if I am listening to the bigger guy, then there is an issue. He is saying that you can have a noise margin of 1.1 volt, but this is saying that you can have a maximum noise margin of 1 volt only. So whose I will listen to? I will listen to this guy only, no? That sir, maximum noise margin in 1 volt. So this guy will also be happy that 1 volt is certainly coming in under 1.1 volt, right? The margin of noise, if I am saying the margin of noise is 1 volt, so certainly that is coming under 1.1 volt, right? So 1.1 will also be happy and 1 will also be happy. So in fan out case, what we took? Minimum. So in this case as well, we will take minimum only. Okay, why taking minimum? Because this shows the margin. So noise margin show that this is the maximum noise you can have, the maximum noise that your circuit can have. Okay, so the maximum noise margin your circuit can have, so that is known as noise margin. So just we will show it now in the diagram. So this is how we represent our noise margin. Noise margin in high state, noise margin in high state, what that would be? VOH minus VIH, and noise margin in low state, that would be VIL minus VOL. Okay. Now this question is asked many times in EAC examination, that you need to tell the order. So you will be able to remember the diagram. No? This is the diagram. Okay. You will be able to remember. You would know that this band is high and this band is low. So from where you would be starting? From here. This band is high. So VOH is the highest voltage. 4 volt, 3 volt, 2 volt, 1 volt. So VOH was the highest, then VIH, then VIL, and then VOL. So this is the order. Okay. So this you should be able to remember, and these are the noise margin. So noise margin high, noise margin low, and final noise margin will be taken as minimum of these two. Let's solve a question. With this it will be all completed. Okay, let's solve this question. Voltage characteristics of a standard TTL gate is given. VOH is given, VIH is given, VOL is given, VIL is given. You need to find the noise margin. So first I will look for high only. Even in case of fan out, in case of noise margin as well, you need to see high. So high. So 2.5 minus 2. 2.5 minus 2. 0.5. NML. Low only. 3 minus 2.3. Wait a second. VIL is low. How VIL is low? Okay, there is some issue. This should be your VIL, right? VIL should be high, right? VOL should be low. VOL should be low. VIL should be high. 3 minus 2.3, that was 0.7 millivolt. So what will be your noise margin? That would be 0.5 millivolt. So for the gate, guys, your syllabus for logic family is completed. If you want to study CMOS inverter, if you want to study more in depth of CMOS, then you can study that. Okay, I will add the videos, you can study that. But if you are not having much time, this much is enough. If you are having this much knowledge of logic family, in roughly around 100 minutes we have covered logic families. So if you are having this much of knowledge, then it is fine. But if you want to study more in depth of CMOS, that also you can visit if you are having enough time. Okay then. So let's meet in the next video. We will study some miscellaneous topic which are left. PLDs we will study, and hazards we will study. Okay. Thank you very much.